So, today we take a slightly different approach to problem solving. So far our approach has been that we are in some given state and we want to find a path to the goal state or something like that, or we are given a description of the goal state and we want to search for a state which satisfies that description. So, today we want to look at a slightly different approach, which is kind of has a flavor of backward reasoning, in the sense you reason from the goal that you want to achieve and try to break down the problem into smaller problems and so on essentially. So, the idea that we want to explore is called problem decomposition. And to motivate why we should use this approach, let me try and take up a problem and solve it in the approaches that we have seen so far. And let us say that you have a friend whose birthday it is, and you have all decided to go out and let us say give a treat to your friend. I know that is not the normal thing, but let us say that is what you are doing essentially. And so, and you have decided that okay, you will go in some time somewhere in the evening, then maybe you will go to a movie or a music show or something, and then you will have dinner somewhere essentially. So, that is the idea of planning an evening. And let us say it is a friend whose birthday it is, whose prerogative is to decide what is acceptable. So, you start querying essentially. So, let us try to visualize this as a search in a simple search space, where you give different options to your friend. So, let us call this problem as designing an outing. And the goal state is when you have decided upon the three things that you will do. What will you do first, what will you do next, and what will you do after that. So, let us say that you start off by saying that you will go to a mall, okay, very popular thing nowadays, and then maybe you will go and see a movie. Let us say I will use HP for Harry Potter, one of the Harry Potter films, and then you will go and eat somewhere. Let us say Pizza Hut. So, I will use PH for Pizza Hut. So, you present this option to your friend and he or she says no. So, that is not acceptable. So, let us say that you are working in a depth first fashion essentially, or something similar to depth first, where this may be heuristically guided or something like RBFS or something like that. So, you try something else, and let us say you give another dinner option. Let us say this well known restaurant in Chennai, Saravana Bhavan, and your friend again says no essentially. And can you think of another restaurant name? So, let us say Coffee Cafe Day, if you can go and eat there. So, which I will use CC here, and your friend says no again essentially. So, let us say you are run out of your budget and your restaurants and so on. So, you go back and say okay, let us try another option. So, just to clarify, this is a evening level, so to speak. This is a movie or entertainment, and this is a eating out. So, there are 3 decisions you have to make. Let us say you offer to go and see Bhuvan Shom, which is a very nice movie, as most of you might know. But and then of course, you can't ask at this level. Yeah. So, in the approach that we have followed so far, we will consider every node and ask whether this node is a goal node or not essentially. And this cannot be a goal node because it has only 2 things, the third thing is not there actually. But there are other approaches, for example, when you do constraint satisfaction, then at each stage of the partial solution you can inspect the partial solution and say is this consistent with what I am looking for or not, but we will not get into that at this moment. So, again you give this offers. So, Pizza Hut, his answer is no, Saravana Bhavan, the answer is no, Cafe Coffee Day, the answer is no essentially. Then you try one more movie, let us say AI the movie. So, you must be knowing there was a film called AI the movie, and then you try these 3 options again. So, I will not write them, but these are the same 3 options that you are trying, and your friend again says no essentially. And let us say at this stage you have run out of movie options as well. So, you backtrack from here and you say okay, shall we go to the beach, and then you try all the same thing again, this entire tree that is below mall you are going to explore below beach again essentially. So, let us say Harry Potter, go to the beach, then go and see Harry Potter, and then go to Pizza Hut, then go to Saravana Bhavan, then go to Cafe Coffee Day, then go to Bhuvan Shom, then go to let us say Pizza Hut, and suddenly your friend says yes, and you have found the solution. Your friend is agreeable to the idea of going to the beach, then going and watching Bhuvan Shom, and then going to the Pizza Hut for dinner essentially. Now, if you look at this search tree, I want you to look at this and make some observations. Is it a good way of searching, or what is happening in this tree? Many nodes are replicated. Or let me ask a more specific question, what is wrong in the left side of the tree? What is it that is not working in the left side of the tree? Where is a fault in the solution that you are constructing, or what is wrong with the solution that the left side of the tree is trying to construct? What is, which part of the solution is not working? Can you look, inspect the tree? So, because you explored the entire tree below mall, and I have drawn 3 movies and 3 restaurants, there could have been many more essentially, and there could be a greater depth. Because you have explored the entire tree below mall and it did not work, if mall was the problem, then you can see that if in the first solution that you considered, which is mall, Harry Potter and Pizza Hut, if somehow you could figure out that mall is a problem, then you would not do all this wasteful work here trying to see okay, if not Pizza Hut then Saravana Bhavan, if not Saravana Bhavan then Cafe Coffee Day, and if not Harry Potter then Bhuvan Shom, if not Bhuvan Shom then AI the movie. All this work is wasted work essentially, and the reason is because the culprit is here. And keeping that choice fixed and searching below the tree is not going to help any longer. Anything you try below this is not going to work if you figure out that mall is creating a problem here essentially. and it turns out that you go this side and then you get a solution essentially. So, how does one solve this problem of doing? So, what is the issue that we want to address is that you have tried one thing and then you are doing this useless work exploring this part of the tree, which will not going to work. Only when you change this it is going to work essentially. So, there are basically two approaches to addressing this difficulty. One is called dependency directed backtracking. Now, the backtracking that we are doing here in most of the algorithms that we have seen is chronological in nature, that you undo the last choice that you make. So, you tried this solution, it did not work, so you undo this last choice which is Pizza Hut and try the next one at that level which is around about. Undo this and try this. When all these three fail, then you undo this and try this. So, this form of backtracking is called chronological, which means that you are undoing the last choice that you are making. What we try to do in dependency directing backtracking is to identify the culprit of what is wrong with the solution, or in other words, without changing that attribute you are not going to get a solution. If you can identify after coming here or after coming somewhere that the culprit is this choice of evening to be spent in a mall, then the algorithm should actually directly jump back to this and try the next choice essentially. So, we will not really explore this option here unless we get time later on, but it is something that we study when you look at constraint satisfaction methods essentially. So, but we are not going to do too much of constraint processing here. Constraint processing is just a different formulation of solving such problems, in which you formulate the entire problem in terms of variables and values that variables can take essentially. The other approach that we want to consider today is to construct what I call AND or graphs or trees. Because we could have converted this into a graph by, instead of generating these three, I could have connected them to these three and then it would have been a graph. So, there is not really too much of a difference whether it is a graph or tree, just a way of looking at it. These are also known as goal trees. So, we want to look at problem decomposition with goal trees, and the idea of problem decomposition is something like using a mechanism to break up a problem into smaller parts. In this example, it is a little bit like using a context free grammar to say that an outing is made up of an evening out and a movie and dinner and then so on and so forth, but it does not have to be context free. In this case it is, but it could be context dependent. So, how do we do this? So, this approach is to view the problem differently, which is to say that okay, you have outing as a, so this is a goal that you are trying to solve, and now you are going to break it up into three separate sub goals. So, one is evening out or evening plan, then movie, and then eating or dinner. So, this is a different representation, and to distinguish between this sort of a tree and that sort of a tree, we put an arc here for our benefit, and such an arc is called an AND arc, and such a node is called an AND node. So, an AND node is a node from which the choices or all the nodes that it points to, it is a directed graph, every one of them has to be solved, as opposed to such a node. So, this is called this we would call as an OR arc, and this we would call as an OR node. So, an OR node has OR arcs below it, and the meaning of an OR node and an OR arc is that you have to do one of the things below that. So, for example, you have to either go to the mall or you have to go to the beach, or if you are if you have decided upon the mall, then you have to either choose Harry Potter or Bhuvanshom or AI. That is an OR. So, we have all those OR choices here as well. So, let us say mall and beach and maybe some other choice, it does not matter. Then we have these 3 choices for the movie, Harry Potter, Bhuvanshom and AI, and then we have these 3 choices for the restaurant. So, this is such a tree is called an AND OR tree, because it has AND nodes as well as OR nodes in them. So, the AND node is at the top level, OR node is below that, and a solution in the OR graph like this, the kind that we have been studying so far, is a path. The solution in a AND OR tree is a subtree. So, a solution will have, for example, this and this and this and this. So, the solution for this same problem is a subtree. Subtree here, the solution in that formulation was a path. The important thing is that you have broken the problem down into 3 smaller problems and solve them independently of each other, which means that when you know that you have to choose between mall and beach, you do this independent of the other things, whereas here one should choose the mall, then you are saying given the mall, what else should I search for. Now, that does not really make sense, because mall is independent of what you are going to do after that, and this formulation of AND OR tree allows you to break up the problem into smaller parts and solve it essentially. So, we want to study approaches to solving algorithms that we will work on such formulations and solve problems like that essentially. But first I want to give some motivation about where it has been used and so on. Now, obviously, there would be cost if you are going to do some kind of optimal solution finding, there would be some kind of cost associated with it, and in this example the cost could be, for example, mall may have some cost associated with it, maybe the distance you have to travel, or sometimes some malls nowadays charge some fees to some people, but I do not know. Obviously, movies also will have charges associated, and eating out will have some cost associated, and you may have some criteria you want to find a solution within this cost or within this budget or of optimal budget and things like that. So, we will worry about cost as we see things later. So, let me take another example. Supposing you want to construct a house, you can see this also, you can pose this problem also as an AND OR problem. So, just to take some simple variations, you might say something like single story or a duplex, these might be choices, and then a single story house may say that you have to make a kitchen followed by, let us say, room 1, so I will just say R1 followed by, let us say, R2 and so on, and let us say balcony. Now, this of course would be an AND node here, and I could have edges coming from here. For example, a duplex house also will have a kitchen and so on and so forth. I can always draw it as a graph or I can draw it as a tree, it does not really matter. Then maybe room 1 would say wall 1 up to, let us say we have 4 rooms, we have rectangular rooms. So, from wall 1 to wall 4, and then maybe door, let us say we have only one door in this, and let us say we have a window. This would be an AND node, and if you look at a wall, for example, you may have choices like stone or brick or mud in some places. So, in this manner the choices that are available to you to construct a house can be organized into an AND OR tree, where at the top level you have the high level goal, which is to construct a house. Then these at lower levels, so this is just a choice here, at lower levels these are sub goals. And then you keep breaking it down. So, till what extent do you break down a problem? You break it down till the problem is so simple that you have a solution already available essentially. So, I will illustrate that with the next example that we see, which is from one of the first systems that was to use AND OR graphs essentially. Now, keep in mind that there are two kinds of costs that are going to be involved. One is a cost of transforming a problem. Let us say we assume that there is a cost of doing that into sub problems, and the second is the cost of solving the sub problem and so on essentially. So, at the end of this, these nodes are called leaf nodes. I mean the leaf nodes are actually called solved nodes. So, the leaf nodes in the tree would be solved nodes, and solved nodes of course would have an associated cost with it. So, depending on the domain, we will see a domain, we will start with looking at symbolic integration for example, which was one of the first applications which use AND OR graph. The solved nodes may not have any cost associated with it. For example, you know that integral of x dx is something that you can just pick up the solution, or x square dx you can just pick up the solution and things like that. But if you look at a problem like building a house, then if you are going to build four walls, then each of those 4 walls, when you build it, it will have an associated cost, and then you will have to aggregate all that cost into the cost of building the house essentially. So, solved nodes may or may not have costs depending on what is the nature of the problem, but transformations will always have some cost associated with them, and that is the way we will look at the problem essentially, because you want to control the amount of search that you do in this tree. Okay. So, one of the first programs to look at that AND OR trees was a program called Saint, which was implemented by a guy called Slagley in 1961. So, when we are looking at the introductory lectures and we are saying what are the achievements that AI has done over the years, then we had mentioned symbolic integration at that time. In 1961, I think in MIT he wrote this was his PhD thesis on how to do symbolic integration. So, what do you mean by symbolic integration is that you are given some expression and you want to integrate that expression, indefinite integral, and you want to convert, you want to produce a expression which is the integral of this expression. So, my mathematics is a bit weak. So, let me just use this breakup which is from his thesis. So, let us say that you want to integrate x raised to 4 divided by 1 minus x square raised to 5 by 2 dx. I am sure you people are more familiar with integration than I am, and you know how to solve such problems. Is that basically you apply some transformations and maybe you break up the problem into smaller parts, something that would fit very nicely into the AND OR situation, because you have a choice of transformations to make. So, first let us look at what the solution looks like. So, this is a node, then you can transform it into sin raised to 4 y by, do not ask me how, but you can do it. So, which you can, so the transformation is x is equal to sin y. So, eventually when you break it down into something which is simple, which is accessible to you, you will have to sort of invert these transformations as you construct the solution for this essentially. I mean, at the risk of converting this into a maths class, let me try 1 or 2 more steps. You do not have to really write this. So, notice that here we have replaced something like z is equal to tan w. So, let me write it here and transformed into this, and likewise this can get transformed into dw. So, now we are assuming that this node is a solved node, in the sense that you can do this without any difficulty. This node is a solved node and this node is a solved node. So, you have the solution now. So, this is an AND node of course, and this so the solution to this integration problem is a series of transformations that you do, followed by breaking up the problem into smaller parts, because we have this addition here, these smaller parts, and then we can solve this integral dw, integral z square and integral dw very trivially. So, we will treat those nodes as solved nodes. So, that is what I mean by saying that the cost of finding such nodes, the cost of this solution is, you can consider it to be small, but the cost of transformation can be counted essentially. But of course, this is not the only way of doing this essentially, and there could have been other choices. So, for example, you could have said that transform this to cot minus 4 y dy and transform this into something else dx, and maybe this does not look so promising or something, or even worse you could try something like this. So, to solve a problem like this, there are many options. So, those of you who remember doing your maths for some entrance exam or the other, you would remember that you have to break your head trying to remember what is the transformation and so on. So, that is why they say you need a lot of practice. But what this program SAINT stands for symbolic automatic integration, and later a guy called Moses developed a program which he called as SYN, because this was called SAINT, which stands also for symbolic integration, and this SYN was eventually transformed into a product called Maxima. And nowadays, of course, you must be familiar that we have this mathematical packages which can do symbolic mathematics for you, and these are all the descendants of this SYN and SAINT essentially. So, MATLAB for example will also allow you to do symbolic mathematics. So, what we want to show here is that symbolic integration can be seen as solving a problem in this manner, where you reason from your large level higher level problem to break it down into sub goals till sub goals are simple enough to be solved trivially, and then you have a solution for solving this problem. Of course, the actual answer to this, you have to undo all the transformations that you have done, which I have not written here. So, let me give another example where this idea was used effectively. So, we had mentioned that in the 70s was the area of what we call as expert systems. And one of the first expert systems was this program called Dendrol. And this Dendrol, so this Dendrol basically also can be some people say you can expand it to a dendritic tree algorithm or something like that, because it generated also an Andor graph which looked like that. But the idea of Dendrol was that it was a assistant it was originally developed as a program to as an assistant to a chemist, and the task that the chemist was doing was to determine the structural formula of an compound essentially. Now, you know that again I presume your chemistry is better than mine. So, you know that if you are given a molecular formula for a compound, for example C6H6 or was it C6H12 whatever, benzene, what is the formula for benzene? C6H6, and you must have heard the story of Kekulé, and you know how people were trying to figure out what is the structure of benzene. So, at a molecular level of course, it has 6 carbon atoms and 6 hydrogen atoms, but the question to ask is how are these atoms arranged in a structure, and that is a very important question, because the physical and chemical properties of the substance depends on the structural formula that sits behind essentially, and to find the structural formula is not such a straightforward task, and apparently Kekulé was dreaming or daydreaming or sleeping or something, and he saw this snake which was biting its own tail, and then he thought of the benzene ring and so on essentially. So, the idea behind Dendrol was to help a chemist find structural formulas, and apparently people who have done PhD in chemistry spend their considerable amount of time trying to find the structural formulas of this thing. And the problem is not so simple, because a given molecular formula may have millions of different structural formulae associated with it essentially, for larger compounds obviously. At a much lower level, you know that structure plays an important role in materials, because whether you are holding a diamond in your hand or a lump of coal, it is just a matter of structure. You are basically holding carbon in your hand, but it is really the structure which gives it the properties that you are looking for. Okay. So, the way this dendrol was implemented, the idea was it will explore the space of possible structures, and this can be done by breaking down a molecular formula into smaller parts and exploring the structure of the smaller parts. You will see a small sample example, but this was aided by a process of generating a synthetic spectrogram. So, there was an algorithm that given a structural formula, what will be the spectrogram of that material look like essentially. Once you can do that, you can compare it with the real spectrogram of the material, and if the spectrogram matches, then you can say you have found the structural formula for that material, and that is the approach which chemists were doing it laboriously. And dendrol was a program, it was developed at Stanford in 1971 or something like that, came a bit after SAINT. It was touted as the first expert system which was built, and 70s and 80s was the era of expert systems, where people said that we will build expert systems, and by this they meant that they will elicit the knowledge of experts, put it into a program, and the program will then perform at the level of an expert. So, apart from dendrol, in the introduction we might have mentioned things like prospector, which was an expert system to find or prospect for oil or minerals and so on. There was a program called R1, which was also at Stanford I think, which was used to configure wax systems. So, in those days of course, buying a machine, a computer was not such a straightforward task as saying I want Apple MacBook or something like that. You had to actually configure various components together, and R1 was a expert system which helped people configure computer systems. We will look at this, how this R1 and things like these such programs were built a little bit later in the course, but today we want to focus on this AO star kind of an algorithm or AND OR tree algorithms, and which basically search over AND OR trees. So, where did the expertise come in? Expertise came in that there was first a program called ConGen. So, dendrol was made up of a program called ConGen, and this stands for constraint generator, and this had expert knowledge inside it. So, of the many possible ways that you could conjure up structures for a given molecular formulas, ConGen was guided by knowledge gleaned from chemists as to what structures are feasible and what are not feasible essentially. So, for example, given a simple thing like C2 H12 NO2, this ConGen would produce a structure like this, or it would produce another structure. So, this is one and this is another one, and there are more examples which I am not drawing here. So, essentially, so again, since you are better at chemistry than I am, you know that this is a double bond and this is single bond and so on. We have not drawn the hydrogen atoms, and you can fill in the hydrogen atoms based on the valency remaining. So, 3 here for example, and 2 here and that kind of stuff, but these are different structures that Congen generates. And what was interesting about Congen was that it generated only feasible structures. So, that is where expert knowledge came into that. So, after Congen you produce a synthetic spectrogram, compare with real, and then you can decide whether you have found the structure of the material or not. And what Dendrol would do is that it would explore this huge space of all possible structures, generates these synthetic spectrograms and compare it with the one of the original material, and eventually do the job for the chemist. And it turns out that this was working of course much faster than real chemists, as you can imagine, and doing equally well or almost equally well. And when you say real chemists, we mean people who have PhDs. So, let me just end with a small example of the kind of space that Dendrol generated, and in the next class we will see the algorithms which are used to explore this space. So, let us say that we are looking at C5H12. So, this is a molecular formula, and any box which has a molecular formula is a unsolved node, or it may be partially solved, as we will see. A solved node is where the structure is entirely given to you essentially. So, for example, it could be like this: C C C C C, and then the hydrogen atoms. So, this would be a solved nodes, as a simple way of organizing this 5 carbon atoms and 12 hydrogen atoms, but there could be other options essentially. So, for example, so these are all directed graphs. You could say that it is C So, a partially elicited structure where part of the structure is known and part is not known. So, 3 carbon atoms are here, 2 are buried inside here, or this is another partially elicited structure, and this itself would have now 3 children which correspond to this part and this part. So, you solve for C2H5 with a bond, then you have another C2H5 with a bond, and then you have CH with 2 bonds, and this is solved, and this can be solved by and this also can be solved by this, and this will have, for example, 2 components. one of them will be this C2H5 with a bond, which will be solved by this, and the remaining will be that whatever remains here C, C, C and so on. Okay. So, in this very quick chemistry lesson, you can see that 3 possible structures for C2H5. One is this structure, one is a structure where you have the middle part where you have C and 2 hydrogen atoms, and the 2 edges contain this structure like this, and likewise this is another structure where the middle part has the C2H5 component. Here the 2 edges have the C2H5 component, so obviously that matters. So, you have either, so one solution is this one, this is an AND OR, another solution is here, and a third solution is that side essentially. Now, what Dendrol is that it navigates this space intelligently, in the sense that this congen component of Dendrol only generates those nodes which are feasible in practice. And how does it do that? It has got a lot of expert knowledge built into it, and that is why this system is called the first expert system that was built essentially. And then of course, it generates a synthetic spectrogram of the, so for example, you take this, generate the spectrogram and compare it with your real material spectrogram, and if it matches, then you know that is a structural formula and so on essentially. Okay. So, today we have just introduced the idea of AND OR trees or AND OR graphs. So, we will not distinguish too much between them, and we have just very briefly talked about the cost associated with solved nodes, and which have to be aggregated into the root node. So, in the next class we will look at an algorithm which explores an AND OR tree or a goal tree to find an optimal solution essentially. So, we will stop here now.